Good afternoon. Can you hear me well? That's good. All right. My name is MAHDY. I'm senior consultant at WSP in the Middle East. I have over 5 years of experience in GCC and MENA region. And my expertise includes tall buildings, embankments, tunnels, ground structure interaction, and I have a sort of solid understanding of the numerical analysis. It's kind of like my hobby. So today's agenda is going to be in the first section, just introduction and context, and then we'll move to our case study, which is the Vail skyscraper, and then we'll move to the inverse analysis of the PTPs, and then the fourth section will be the settlement control, and fifth will be the conclusions. So the introduction and context, but before we go to the introduction and context, I'd like just to give a heads up about WSP. WSP is a global consultant that is, oh, is it working? Okay. Yeah. We have offices everywhere, but here in the Middle East, we have 8 offices. Some of them in KSA, some of them in here in UAE, and we have in Qatar, and also we have 1 office in Oman. And this is, over the past 10 years, we have worked on remarkable projects. As you can see, this is a part of WSP City. It's not the full projects that we've worked on. No, this is just a part of it. And today's subject is going to be that tower that you can see in here. And actually, this is Dubai's thinnest skyscraper. This is the most slender tower in Dubai. And actually, it's the second most slender tower in the world. So about the development location, it's located exactly at the intersection of Dubai Canal and the Sheikh Zayed Road. As you can see, it's highlighted in this slide. We can go over some of the key facts about the project. It's an 80-story tower that is standing almost up to 400 meters above the ground level. And as I keep saying that it's a very slender tower, let's define the slenderness, because I know that this is a terminology that is not familiar to most of us here. So the slenderness from a structural perspective, it's the width of the building, the ratio between the width of the building to its height. So the ratio here, it's the height of the building, it's actually the height above the ground level, because the slenderness, it's actually a structural measure, not a geotech measure. So in our case here, it's 18:1. And let's put that into perspective and have a look at some of the key projects in the world and what is the slenderness ratio that we have for some of the projects. You can see on the very right-hand side, this is a pencil that is slender. And the slenderness ratio for that pencil, it's 1 in 27. Next to it, there's the most slender tower in the world, which is the Steinway Tower. It was designed by WSP also, and it's in New York. And next to it, that's the second most slender tower in the world, and it's here in Dubai. This is the Vail. Now we move to the technical stuff. We'll start with the site-wide ground model. It's a very straightforward ground model. We were lucky as geotechnical engineers that our geology in this site, it was almost uniform, which is not really the case for most of the projects, but we were super lucky in this project. You can see that the foundation level is minus 26 meters DMD. That's the top of the raft that you can see on the right-hand side. And if you have a look at the UCS, which is the unconfined compressive strength of the rock mass that you see, it's actually situated in the weak rock zone. So actually, it's a weak rock. So actually, we're interested in 2 layers, the layer from minus 25 down to minus 50, and from minus 50 down to minus 85, and downward. Below that, we're not really interested in that, but that's actually a very stiff mudstone layer. So on the prelim design, it's actually a preliminary design. That's why it's handwritten. But anybody who picked that design up and tried to design the foundation, he would think, of course, about the piles. Why don't we get to piles? Okay, so as it's a prelim design, we need to first determine the length of the foundation that we can use. And it's actually the standard practice that we have in here. We compute the ultimate skin friction as a 0.3 times the square root of UCS. And if you do that, with a load demand of 71 meganewtons, you end up with the piling length from the ground surface, because we have the ground level above the 2.25 meters from the ground surface. So the total piling will be like 120 meters. Of course, no contractor will accept that because they will have hardships on site. That's really impossible. But we can think of the barrette, which is the solution on the right-hand side. We end up with the total piling of 85 or 86 meters, which is quite promising because the quality assurance on site on the barrettes is way better than the piles. This is one reason, and the other reason for going to the barrettes is going to be explained later. And in comparison between the prelim design, which is the one in the middle, and the detail design, which is the one under construction right now, which is on the right-hand side, you can see the prelim design has a 367 barrettes, but the detail design has 314, which is, you can see that there's amount of savings, significant one, not only on the number of the barrettes, but also on the total length of the barrettes. And in summary, we managed to achieve like a 40% on the total piling length or barretting length from the prelim to the detail design. And also in terms of the environmental issues and the carbon emissions concern, we also managed to save almost like 10,000 tons of carbon emissions per year. So the question that can be raised right now, how we managed to achieve that, how we moved from the prelim design to the detail design, because there's a lot of savings in here. So like many of the projects that we do here in Dubai, we have PTPs. This is a mandatory requirement by Dubai Building Code, but I'm sorry. So actually in our PTP program, we had two PTPs. We were concerned, the first PTP was 1,200 millimeters by 2,800 millimeters. And we were concerned that we may encounter a certain overstressing that we have to go for a greater barrette. So we added one barrette to the PTP program that you see in here. So we had two barrettes, but each one of these were instrumented using two O cells. And you can see on the right-hand side that this is the measurement for load cell number 1 that you see in the layer from minus 30 to minus 50. Excuse me, I need to drink some water. I'm sorry. Apologies, the weather is hot and I'm kind of dehydrated. All right, so we can resume. So we had two PTPs on site. Each one of these were instrumented using two O cells, and this is the raw measurements that you see. You can see that the skim friction mobilized inside is reaching 13 and 1400, which is a very high skim friction to have mobilized on site. So I have a very long story to tell in here, but I will try to summarize it as much as we can. So what you see on here in red, this is the state of practice range for the ultimate skim frictions that most of GIRs give. So you can see that it's quite low compared to the maximum mobilized skim friction that is on top there. And yesterday there was a panel on the over-conservatism. This is one of it. And we cannot actually use the maximum mobilized skim friction because the mobilization of skim friction, it is dependent on the amount of load that we have, so we had to define a state of geotechnical rupture, which is the skim friction mobilized at 300% of the load that was this barrette designed for. So this is the two 2 points that you see in here. The maximum mobilized skim friction, it's almost 1,000 kilopascals. And if you apply the Eurocode factor or the Eurocode methodology that you see in here, it reduces to two characteristic values. And if you try to fit these 2 points using that capacity model that we've been using here in the market, it will give you, actually, you can fit it using two capacity models. The first one is the lower bound, which is the red one that you see in here, and it's given a beta factor of 0.42. And you can fit the second point, which is to the left, and it will give you a beta factor of 0.56. And if you take the mean out of these, and you can use that for design, of course, but it's going to be based on the Eurocode, and you have to follow the Eurocode convention for the design, you can come up with a factor of, with a beta factor of 0.5. So actually, when we started doing the design, the ultimate skim friction was computed as 0.28 to 0.32. That was mentioned in the GIR. With a load demand of 71 meganewtons, you can see that the required barrette length is almost 51 to 55 meters. But the mean Eurocode-based design, it's 0.5, and I will give a length of 27 to 32 meters, depending on which design combination from the design approach number 1, because that's the one recommended here in the building code. But we ended up with a detailed design model of 0.42 times the square root of UCS. I'm not going to expand on this one because that one is actually pretty detailed to explain in here. But this is a numerical back analysis for the ground parameters using the O-cell test. So a numerical model was set up in Plaxis 3D, utilizing the symmetry that you see in here, and using the boundary conditions in that, and using that ground profile. We've done a lot of iterations just to reach to what are the actual ground stiffness that we can use in our design. And the discrete data that you see, this is actually the small strain modulus that has been measured on site. And the red one, this is actually the design one that we have adopted. But the black profile that you see, this is the stiffness profile that was revealed by the back analysis. So you can see that what we have used, or what we have concluded to, that's the red one, and the actual one, I would name it the actual, it's the black one. So given that this is actually a super slender tower, so the structural concern here is the lateral displacement of the building, because that's what the structural engineer really care about. And this is actually a geostructural problem. It's not just a geotechnical or structural problem. So we have to do some analysis to come up with the lateral stiffness of these barrettes. But we first have to identify the most critical cases for the design. I'm sorry, I need to drink some water again. So our tower, it's slender in one direction. It's a very strip in one direction, and in the other direction, it's very slim. So we have two critical cases. When the wind is going in that direction, which is from the left to the right, the y direction, we can have a delta displacement as a maximum displacement at the top of the tower. If we reverse that load, the foundation behavior will be different, as you can see it in here. And also that you can see down there, it's the determinant of the structural and the foundation stiffness with the mass of the structure. If we give the structural engineer a set of stiffness for the foundation, and then we change it, of course the dynamics or the dynamic properties and the vibration properties of the building will change. So that's why we had to do the analysis for a 2-wind tunnel, not only one, because this is actually super critical for the slender structures. The question now, how can we come up with that? Because think of the loading as the building is standing there with its own weight and some of the people living in there as a live load, and the wind loading is coming over day and night. So if we think of that, that could be defined as this very simple problem. So the building is there as a stage 1, it's deforming under its gravity loads, and then the wind load comes. And on the very right-hand side, this is the response or the reaction of the base due to only the wind. One engineer could think of, I'm going to apply only the wind loads and compute the stiffness, but this is really true only if the foundation behavior and the soil behavior is completely linear elastic, which is not the case in here. So we have to do something about it and do it in stages, simulating what's happening in reality. And in one phase, we apply the gravity loads, and then we apply the lateral loads due to wind, and then we compute the stiffness. But the question here, which stiffness that we're going to compute? It's going to be the force over displacement? That's actually not true, because somehow you have to compute the representative stiffness for the foundation response when the wind load comes. So it's going to be the tangent stiffness between phase 2 and phase 1. Which reflecting only the structural or the foundation response when the wind load is applied. And what you see on the left-hand side, this figure, it's very simple. It's drawn for 2 nodes in here when we have the load in that direction. But when the load is reversed, that approach is going to be applicable and it holds valid. So now we come to the third section, or section number 4, I'm sorry, which is the settlement control and barrette design. So how we manage to control the settlement with the assumptions on the soil structure interaction formulations that we have in literature and implemented in the software that we use on a daily basis. So actually, we started with the plate and embedded beam model, and this is the model that we have developed over one of the stages. But one thing here that I want to highlight is the rotation of the local axes so that it could match with the principal axis of the section, because barrettes are not piles. Pile is a very good structural element where you have the inertia in one direction is exactly the same as the other direction. But when it comes to barrette, you have two different, or actually infinite number of different structural stiffness, and of course you will have an infinite number of different geostructural stiffnesses. So you have to align the inertia of that structural element with the local axes so that you can ensure that the structural stiffness is properly defined and you get the right or the most proper shear and bending forces. But let's be aware of the embedded beam element. I'm not going to list all of the embedded beam element approach as in here. I really admire the approach. It's been developed since 2004 and it's been developed until today. Even in the next version of Plaxis, there will be a new embedded beam approach just to improve what we have today, because what we have today is actually limited. It's not addressing all of the soil structure interaction assumptions that we have. But the main assumption or the main limitation that we should be aware of, the embedded beam is just a line, and the behavior of that line or frame element or beam element is being coupled with the surrounding soil by discrete springs. And actually, within the model, there's elastic area, and that elastic area in Plaxis is assumed a cylinder. Meanwhile, in our reality, it's not a cylinder. You can see it's actually a rectangle. So this is one of the limitations that we have to be aware of. And there's another limitation that is not really applicable for barrettes, which is the axisymmetry of the assumptions on the soil structure interaction. That could be actually valid for the piles, but not really valid for the barrettes. And let's have a look at the barrette soil behavior under lateral loading. So actually, if you have a barrette and you try to push it laterally in a direction, you will get a displacement under the same force. But if you reverse the direction of the force to be normal to the first one, it's going to be a very different behavior. Embedded beam element cannot really capture that. So what should we do? We have to get back to the fundamental or the standard modeling approaches of geostructure, which is modeling things as continuum. And so we had to develop that model just to verify our assumption on what we have done using the embedded beam. Is it going to be really conservative what we have done, or it is valid? So we have developed that really complicated model. And we had to ensure that the quality of the finite element mesh, because actually it really matters here. So Plaxis defined the quality of the mesh as the ratio that you see in here, which is the Jacobian of each one of these elements, each one of these finite elements. And the reason why we care about the quality, because it goes to the formulation of each one of the finite elements that you see in this problem. So actually, the finite element mesh that you see it's quite of high quality, because 60% of the elements achieving like more than 70% percentage on the quality. Drink some water again. So one of the fundamental assumptions in the embedded beam element, there's some certain formulation in that element that is prescribing how that element is interacting with the ground. But actually, in this case, it's really different. You have to prescribe the interaction of the element that you're putting in the ground with the surrounding soil. So this is a schematic showing what we have done. If you have a if you have a barrette element, you have to include some interfaces, but you have to do something really special about these interface elements. It should be slightly extended for a reason. As a matter of fact, the stresses in the finite element, they're discontinuous, unlike the deformations, which are really continuous and smooth. And that point, which is at the pile toe, if it's not actually split into 4 points like the one you see in here, you're going to end up with a stress overshooting, and that will overshoot your pile capacity. So we had to extend the interfaces, as you can see using the scheme in here. And also, just in line with the local practice, we had to introduce some elements at the toe just so that we can suppress the end-bearing resistance of these barrettes. And this is actually the material model that I've used or selected just to represent the ground structure interaction. So it's actually a plastic dilation suppressed linear elastic, perfectly plastic, with zero post-peak shear and tension behavior. So actually, this interface does not carry any tension. And once it reaches the peak value, it goes directly to a residual value of almost 0. And this is actually conservative. And one of the things that we should be aware of, you cannot control the actual pile capacity or the barrette capacity when you're doing it as volumes. But if you're really concerned about that, of course, you can use that material model in gray. It's very simplified, and you can put the skin friction, maximum skin friction that could be mobilized in that element. And if you're not really happy with that, but I've selected the one that I've drawn in blue, and I verified that the maximum skin friction mobilized in that model, it's actually less than what we had in the PTP. And regarding the settlement, you can see that the settlement is 48 millimeters. That's the maximum one, and it's exactly or more or less at the center of the tower. And you can see that the minimum settlement is there at the corner. This is the podium, and it's 4 millimeters. And you can see also that the settlement at in that direction is 90 millimeter, and here it's 14 millimeter. And of course, we need to verify that we have done initially using the embedded beam, which I've explained the limitations of. Firstly, so let's put things into comparison. So I'm sorry that the title is not really correct. So this is the raft settlement embedded beam versus the continuum model down there that you see. So the embedded beam element, we know that it is conservative. There are some assumptions. And these assumptions revealing, or on the conservative side, the maximum settlement is actually 52 millimeters compared to a 48. So we have a 48 millimeter. And this one is satisfying the limit dictated here locally, and this one is actually not. And on the corners of the tower, you can see that the maximum settlement predicted by the embedded beam is 20 millimeters, but the one with the volume elements, it's 14. And also for the for the podium, the minimum settlement predicted by the embedded beam, it's 8 millimeters. Meanwhile, for the volume elements, it's only 4 millimeters. But actually, the question that I see in some people ask right now, did you use that model to verify the straining actions that you get in the barrette? That's actually true. We've done that. As far as I admire Plexus, I've been using it for almost 10 years, but every software that we use has limitations or assumptions internal in that software. And to retrieve the structural forces from Plexus using that tool that you see down there, it has certain assumptions and also limitations. So the first limitation, your pile or your geostructural element has to be uniform and circular shaped, and it applies only to vertical elements. If you have an element that is inclined or raked pile, it's not going to work, actually. It's not going to give you like really correct results. So what's the solution? So you can insert a very weak element in the middle, and that will give you the forces. Of course, it's going to give you the axial force correct only if the element is vertical. But it's not going to give you the right results for the bending or shear forces. The other option is you can go and take a cross-section at the barrette cutoff level and compute the resultant forces, because actually Plexus is reporting that, which is the right-hand side figure that you see. But you will have to do that for each and every barrette, which is 314 barrettes. Of course, you're going to do that, but over 1 week. I don't think that's really practical. The third solution is you can do one thing that is the proper solution for this problem. You can read the finite element mesh. You can read the location of the Gauss points and the stress tensor at each one of these points. And you can do some some numerical integration on these stresses to compute the forces that you need to verify your reinforcement or compute your reinforcement against. So actually what you see in here, this is a complete algorithm that has been specifically developed for this problem so that we can compute the forces. I'm not going to explain that, but think of it as you have a finite element mesh over a certain volume. You take multiple cross sections, and over this section you compute the resultant force and also the bending moment, not the bending moment, I'm sorry, but the moment of that force about the centroid of that cross section, which could be easily computed using the boundaries of that cross-section. And on the right-hand side there, you can see that if you compute the resultant, and you know the orthonormal basis, which is the local axis orientation with respect to the global axis, you can compute the straining actions and take it for the designer's forces. And also, if you have the moment, the moment or the resultant moment of that resultant force, of course, you can compute the moment. And the math looks really fancy. I like it. I really admire it. But does it really work? Of course it works. But let's make things really simple. So we take just a column that is 30-meter high with the same dimensions of the barrette. We just fix it at the boundary down there. We apply some forces, and these forces we can compute the axial force, the shear force, and the bending moment using hand. So it's actually a problem that an undergraduate can handle and compute the forces based on these forces that we have applied. If you have a look at the top figure, just let's forget about the figure down there. The top figure, you can see that the axial force, the numerical, which is the one following the algorithm that has been developed, and the analytical, they're exactly on the same line. It's the same thing, okay? And if you compare the shear forces, it is exactly the same thing, and also the bending moment you can see. And by the way, the bending moment here, it can be computed by hand, which is W, which is the intensity of that load that we have applied, times the height to the power of 2 over 2. And it will give you exactly the same value down there at the point of fixity or the surface of fixity that we have applied. So the conclusions and takeaways of this: for slender towers, you need to actually coordinate with a structural engineer closely because you need to verify any assumption, because if your foundation just moves 1 millimeter down there at the bottom and the stiffness of that structure is actually, compared to the height, it's actually very low, the structure will sway. So actually that millimeter will be very, very high lateral displacement when you reach to the top of the building. And the value engineering, you have seen that we have managed to save at least 40% of the preliminary design, which means that it's millions of dirhams in saving. And you can always use the high fidelity numerical analysis just to verify your design assumptions or limitations, in other words. And thank you.